Okay, so my research was about visualizing interpretability for precipitation prediction using Shapley additive explanations. So basically tackling interpretability using like visualization. So as deep learning has been used more for climate simulation research, we've encountered an issue, which is that neural networks are generally very uninterpretable, which means that they're black boxes. We're putting garbage in and we're getting garbage out. And so what we need to do is well, the issue with that actually is that data set and representation biases can be hidden in black box models. And we could also be missing results that we need. For example, like if a certain input variable is influencing a certain output variable, and we don't know about that because there's just so many variables, that's an issue that we would have. Right now, there is a large body of literature concerning how we can tackle interpretability in different models. And there's also ways to visualize this. Trustworthiness and reproducibility are influenced by interpretability. We need interpretability to actually trust the results of the model. And so that's why we tackle this. The Clemson paper recommends looking into interpretability, and it recommends using dimensionality reduction and symbolic regression. We take a slightly different approach using visualization, which is an important aspect of interpretability. Here's like some other work I did before. We basically looked at infrastructure damage, assessing that after natural disasters using computer vision. And you can see here that we also used visualization to see which part of the building contributed most to that prediction. Specifically, we're looking at precipitation here, and that's correlated obviously with many variable conditions, many of those variables which are included in the Clemson dataset. What we want to understand is which variables matter most and contribute most to precipitation. So the methodology consisted of first pre-processing, so focusing on certain variables for training, slicing the data set along those variables. We looked at all columns, so like latitude and longitude, as well as we taking the daily mean of the data so that we don't have too many data points. We trained 4 different residual neural networks, or ResNets, based on different loss functions and input combinations. And we visualized the importance of 3 inputs on 1 ResNet model using Shapley additive explanations. Shapley values are based on game theory, and you can see here that the main components of it are the weighting of a certain input data point as well as its contribution. And then so we multiply those, and then we sum it up across all different input data points. There are 2 variations of SHAP that we explore: Deep Explainer, which is more suited for convolutional neural networks, and then a model agnostic version. And then we compared results with weighted SHAP, which is supposed to have certain benefits. And so the pre-processing is very straightforward. We combined rain and snow rate for total precipitation. We sliced the data set along those variables I discussed. And then for variables that are vertically dependent, we looked at the middle 20 levels. So the ResNet 50 model architecture is special because, well, ResNet as a whole solves an issue with neural networks that is called vanishing or exploding gradients, which is that when you keep adding layers, oftentimes the gradient will go to 0 or it'll explode. And so what we need to do is have residual blocks, which employ skip connections. So an activation from a certain layer will be connected to another future layer by skipping layers in between. And then so we have a lot of those pairs or residual blocks throughout the ResNet 50 model, which is called that because it has 50 layers. So we have like pairs of like convolutional blocks and identity blocks. And then at the end, we have average pooling, flattening, and fully connected. Okay, so we trained 4 different models, evaluated on F1 score, which is the harmonic mean between precision and recall. And then so one model, we take the input being cloud liquid mixing ratio, surface pressure, specific humidity, the output being total precipitation. The second model, input being air temperature, ozone volume mixing ratio, and solar insolation, and also having the same output. We used also 2 different loss functions. One is mean squared error loss, and the other one is cross entropy loss. Comparing all 4 models, the one that is the most accurate, you could say, or has the best F1 score is the one on the top right. And that's the one we use for evaluating interpretability because we want to be using a model that is more accurate, ideally. So SHAP versus weighted SHAP. The original SHAP methodology is connecting optimal credit allocation with local explanations using the classic Shapley values from game theory, which I just explained before, how it's talking about weighting and contribution. And then the limitation of SHAP, however, is that it assigns uniform weights to all marginal contributions, which means that if you have a lot of features or not many features, it's not going to like differentiate that actually. So what weighted SHAP does is that it does make a difference there. It learns to pay more attention to the marginal contributions that have more signal on a prediction, and assigns larger attribution to more influential features, which is ultimately what we want if we want to have interpretability in machine learning. So here are the results from that. The deep explainer, the one that combines deep lift, which kind of like back propagates all the neurons in the neural network to all the features in the input. So it combines that with SHAP values. So basically it uses Shapley equations to linearize components like softmax. And then uses a distribution of background samples. So what we see here in the top graph is that cloud mixing ratio has a very like noticeable positive impact on precipitation, while specific humidity and surface pressure seem to have a negative impact. So what we can see from this is that when we have more cloud mixing ratio, less specific humidity and less surface pressure, we get more precipitation. And then the second graph, we focus on cloud mixing ratio specifically, and we see that when the cloud mixing ratio goes up, precipitation or the SHAP value for the influential measure of cloud mixing ratio on precipitation goes up. But I don't think the ticks might not be correct on that. The kernel explainer is a model agnostic method, uses a specially weighted local linear regression to estimate SHAP values for any model. So the top one shows cloud mixing ratio having the highest positive effect on precipitation, with surface pressure, with surface temperature and specific humidity having slightly less. And then the bottom graph here is actually using a different model where we train on like a lot of different variables. We could see that on the first 2,000 predictions, we have like some variance in the SHAP values. Okay, and then finally we use weighted SHAP. So the difference between this is that there's a metric that the weighted SHAP paper proposes, which is area under the prediction recovery error curve, or AUP. And so that basically sums up the absolute value between the difference between F hat, which is like the prediction minus the conditional expectation, which is like that second expression there, and you add them up, the lower the better. And so we see like weighted SHAP, as we add more features to the model, performs increasingly better than Shapley, even though it even started better as well. So basically, cloud mixing ratio, surface temperature, specific humidity have like decreasing magnitudes of effect in that order based on the model agnostic method. Based on the deep explainer method, it seems that like more cloud mixing ratio and less of the other two have more precipitation impact. And then the weighted SHAP approach is somewhat more effective, but like more like exploration needs to be done on that front. And then, yeah, finally, next steps would be applying other interpretability techniques on CNNs and other models, applying the same pipeline to different input combinations. The combinations that I use in my models were like somewhat random because like I had limited time and I didn't have time to train more models, but that's probably not the most ideal input combination. Optimizing the CNN itself more because like 0.8, like it's not like that good. And then also trying the other methods suggested in the Clemson paper. So yeah, that's it.
We'll take questions in the room, and if anyone has questions online, please use the Q&A function or raise your hand and I will unmute you. Anyone in the room?
I had a question about the credit allocation. Can you go back to the slide with the expectation? Yeah.
Wait, this one, yeah.
Yes. So I guess I was just hoping to learn more about how like this is evaluated, and particularly about like the scale of like the y-axis. Like, does the fact that the difference between the actual and the expected value is like so small, like significant? And like, yeah, can you just tell us more about like how one might like make sense of like the y-axis to that plot, and whether it's like relative to something, or just whether it's like a really good sign that those values are super low.
Like the specific values here?
Yeah, for the AUP. Yeah.
Yeah, I guess it does show like that my model like itself was pretty good, that like the expectation and the prediction were very close. But to be honest, like I'm not like fully in understanding of like the theory behind this, because this was like kind of the last part of the project, and I didn't really look into like exactly how that conditional expectation is calculated. But yeah, I think that smaller values are better. Yeah.
Yeah, I have a question on the same slide.
Sure.
So I can see that when your feature number is around 9, you kind of the weighted shape kind of helps the prediction much better. Like, and first is, did you include the vertical variables for this work? And do you remember which are the features for the 8 or 9 vat?
Yeah, actually so like for the vertical variables, I kind of like the reason why it's so many features is that I split it up into like different levels. So like the variables will be split into like the top third of the levels and then middle and the bottom. That's actually a really good question, like understanding which variable was like right here, and I could like easily find that out like if I go back to it, but I didn't have enough time to do that analysis. Yeah.
Okay, great work. Yeah, thank you.
Thanks.